Welcome everyone to this LCN lunchtime seminar. I'm Marlon Schaffer. I'm the previous co-director of the LCN. I'm standing in for Sandrine, who sent to apologise. We're very happy today to have Alex Ganose giving our seminar. He is an EPSRC Research Fellow here at Imperial, and he's working mainly on studying renewable energy materials. But he has a good connection with the LCN, having started in UCL before then spending time in Lawrence Berkeley National Lab. And although he's at a fairly early stage of his career, he's already a fairly stellar record of accomplishments, including a very large number of papers, over 40 papers and about 2,000 citations, and has been working hard on data-driven methods, electron transport, and various kinds of lattice dynamics. And he's got an interesting title today, which is a very open-ended one. So I'm interested to hear what you've got to say, Alex, on what we can learn from the temperature dependence of carrier mobility. So over to you.
Thanks very much, Marlo. Thanks for the introduction. Thank you for inviting me to talk here today. It's a real pleasure. I'm Alex. I'm a research fellow at Imperial in the Department of Materials. Today I'm going to actually be talking about some work that I started while I was a postdoc at Berkeley Lab. And I was really interested in looking into the transport properties in semiconductors. And I'll just give you a bit of background why we were kind of interested in this topic. And it really came from our interest in thermoelectric materials. So these are materials that can convert waste heat into usable electrical energy. And the idea really is that we can use them to scavenge waste heat and then, for example, around car engines, convert that to electricity and then use that to kind of get more fuel efficiency out of a car. And I'm a computational chemist, computational materials scientist maybe. And I'd say that really thermoelectric materials have been a very challenging problem to approach from a computational point of view. In thermoelectric materials, the way we evaluate them is through this figure of merit, or the ZT. And this has several properties in it. It has the Seebeck coefficient, which is alpha here, the electronic conductivity, and then also the thermal conductivity. And what we find is that part of the reason why it's difficult to find new thermoelectric materials is that these properties are almost antagonistic. When you optimize one, it generally reduces another one. So here I'm showing carrier concentration against ZT. And what you can see is that if we increase carrier concentration, we increase our conductivity, which is this red line, but at the same time, it reduces our Seebeck coefficient. And what we end up getting is quite a complicated behavior in the ZT with carrier concentration. And it's turned out that it's very difficult to predict computationally where the peak of this ZT is going to be and how high we can actually get it. And just to illustrate how difficult this has been, this is just a summary of all the materials to date which have been computationally predicted, but then went on to actually be experimentally verified. So I actually made this in 2021, so maybe this is slightly out of date now, but in 2021, there were only 9 materials that had ever just been computationally predicted as thermoelectric materials. And here I'm showing the timeline and the experimentally measured ZT. Now, for a thermoelectric material to be viable, we really need ZTs above 2 and ideally beyond 3. And you can see that basically across all of these materials, the best ZT we were able to achieve was about 1.6. So we're well below what we really need. And in a thermoelectric module, you need both P and N-type components. And you can see that if you look at the N-type materials that we found in blue, these are really poor performing. So they only get ZTs about 0.8. So we have a lot of work still to do. And I think part of the reason why this has been so difficult comes down to the difficulty of calculating electronic transport properties in a reliable way. And so when we're calculating transport properties, one of the most common approximations and ways of doing this is using the Boltzmann transport equation. So this is considering, I say carrier transport, which means kind of free carriers available through doping. And when we're calculating the Boltzmann transport equation, there's 3 properties that we're really interested in that we need to calculate. That's the group velocity of our electrons. So what's their velocity? The energy of the electrons, and then their lifetime, how long they can travel for before they scatter off something and change direction. Now, the group velocity and the energy are very easy to obtain. We get them for free just from a density functional theory calculation, which is just kind of a standard calculation in our toolbox. But the lifetime is very difficult, and it's really where almost all of this complexity lies in obtaining transport properties. So the way we obtain these lifetimes is through Fermi's golden rule. I won't go into too much detail, but the gist is that if we want to calculate the partial decay rate from one band at one K point to another band at another K point, we have to use Fermi's golden rule, which depends on this matrix element. And this matrix element takes into account the overlap of the initial and final states, and also the perturbation due to a kind of scattering potential. And so the difficulty is calculating these matrix elements. And part of that is that there's many different scattering potentials that we have to consider. So you can have scattering of electrons due to vibrations in the crystal, due to impurities, grain boundaries, and things like that. Now, over the last 50 years, there's been a hierarchy of methods that have been developed for calculating these electron lifetimes. So the most commonly used and the most basic is what's called the constant lifetime approximation, where basically you don't bother calculating anything, you just set the lifetime to a value. Maybe it's the average of some materials that you measure experimentally. And so the benefit is that this is extremely quick to do, and because of that, it's very widely used. But as you can imagine, you're using a fixed lifetime for every electron, which isn't correct. And you're also choosing an arbitrary value. And basically what this means is that any mobilities that you calculate or any transport properties that you calculate using a constant lifetime, they're again just going to be arbitrary, and you could scale them just by adjusting this lifetime. So we can do a little bit better than this, and that's by using approaches which try and model physical scattering mechanisms. So one of these is called the inverse density of states approximation. And the idea is that you just set the amount of scattering proportional to the size of the density of states, which is just saying that if you have more states to scatter into, you'll have more scattering. And so this is, again, has the benefit that it's very quick, and it models an actual physical scattering process. So this is acoustic phonon scattering. But again, this is you still have an arbitrary element of this, because you still kind of got to choose the reference lifetime from which you scale your scattering rates. And you're kind of if you use this approach, you're kind of deciding in advance that actually acoustic phonon scattering is dominating in your material, and you're kind of imposing a scattering mechanism which might not be correct. So on the other end of the spectrum, we have methods based on density functional perturbation theory combined with Vanier interpolation. So these are really state-of-the-art approaches, which has really been developed in the last 10 years. And they're extremely accurate, and they're fully first principles methods. And we can really see kind of mobility and transport properties within about 5% of experiment using these methods. So they're great, but the downside is that they're extremely expensive to run. So I'd say that for most practical calculations, you're probably limited to about less than 15 atoms in the unit cell. You can go to higher, but it's going to cost you a lot of computational time. So in this work, what we wanted to try and do was bridge these two regimes, and so try and get the accuracy close to these density functional perturbation approaches, but with maybe the computational cost of some of these cheaper methods. And so that's, I'm happy to say that we succeeded in doing that. And so while I was at Berkeley, I developed this approach called AMSET, where we explicitly calculate scattering rates so we get the accuracy of basically DFPT plus Vanier at about 1/500th, or I'd say close to the accuracy of DFPT plus Vanier at about 1/500th of the computational cost. And the way this works is we take an ab initio band structure, and here all the calculations that I'm presenting were calculated using the Vienna ab initio software package. So we take a band structure, calculated using DFT, we interpolate it using Fourier interpolation, calculate the k-point dependent scattering rates, and then we go on, and I'll go into this a little bit more detail in a second, but the gist really is that there's no fitting parameters used here. Everything that goes into this calculation is obtained from first principles. And then we solve the Boltzmann transport equation to get transport properties, so conductivity, mobility, Seebeck, and thermal conductivity. So the trick in AMSET is that we're using computationally cheap matrix elements that rely only on common materials parameters. So there's a range of scattering mechanisms that we can model. For example, acoustic deformation potential scattering, which depends on the deformation potential of our material and the elastic constant. Impurity scattering, which depends just on the dielectric constant. Piezoelectric scattering, and also polar optical phonon scattering, which depends on the dielectric constant and phonon frequencies. Now, the thing is, all of these properties that I mentioned here that you need to calculate these matrix elements, these are all really readily obtainable just from routine first principles calculations. So none of these are expensive to obtain. So how well does AMSET do? This is just some results on gallium nitride. So here I'm showing temperature against mobility. The experimental values are these black triangles, and the AMSET results is this black line here. And I should just add that these experimental measurements which I've taken, these are very high purity single crystal measurements. And so we've really got, we're minimizing the kind of other sources of scattering which could limit our mobility further. So you can see that there's really nice agreement with AMSET across the entire temperature range. What's also nice is that we can actually decompose this mobility into the contributions from the individual scattering mechanisms. So that's what I'm showing here by these colored lines. So with this teal line here, this is scattering if we only, this is the mobility if we only consider ionized impurity scattering. And then here, this is a polar optical phonon. And you can see that there's a kind of crossover between these two mechanisms at about 300 Kelvin. And actually in the experimental mobility, we also see a kind of change in the slope of the mobility around that point as well. So I think it does capture quite nicely the experimental results. So this calculation I'm showing here was done, as I said before, using only first principles inputs. There's no fitting. And this entire calculation took about 10 minutes on my laptop once I had all the inputs. So just for comparison, if you wanted to do this using some of these DFPT approaches, that's going to take you tens of thousands of hours on a supercomputer to do a comparable calculation. And you actually get a lot of information. So here you can actually resolve this, this information down even further to look at the K-dependent or the state-dependent scattering rates. And so here I'm showing the energy of the electronic states against the lifetimes. And so this point around here is the conduction band minimum. And what you can see is that around the conduction band minimum, the scattering is limited, or the lifetime is dominated by impurity scattering. And then as you get deeper into the band, at some point, polar optical phonon scattering takes over. And actually what we see is that this transition happens at the phonon emission temperature. So at this point, you start getting both absorption and emission of phonons, and it starts dominating at that point. So this is just some more comparisons to show you that we actually do perform pretty well compared to DFPT plus Vanier. So this is three materials: gallium arsenide, silicon, and tin selenide. And here I'm showing AMSET in blue and these DFPT plus Vanier results in red, and again, experiments shown by the black triangles. And you can see that basically we're really in the ballpark of DFPT plus Vanier across the board. The other thing which is nice is that we can really take into account anisotropic properties. So tin selenide is relatively anisotropic. Here I'm just plotting the results for the B-axis, and you can see it agrees pretty nicely. And I'll just highlight this gray line here, which is the constant relaxation time result. And you can see that with this approach, you really get these results wrong in both magnitude and also the temperature and carrier concentration dependence as well. So it's a really not a robust theory to use. We tried to screen a few more materials. So here I'm just presenting a summary of 21 materials that were calculated using AMSET. I'm showing experimental mobility against calculated mobility. And again, we kind of see very nice agreement across the board. I'd say that these results were calculated using PBE, which is a relatively cheap method. Well, the electronic structures, sorry, were calculated using PBE. When we go, there's a couple of outliers here, and actually these, when we go to a higher level of theory to calculate the electronic structure, this gets a much more accurate effective mass, and these points drop down onto this line here. And again, we also did calculations against Seebeck coefficient, and again, there's a nice agreement across the board. So AMSET is an open source package. It's developed in Python. You can just Google AMSET and start using it today. It should be very easy to install and run. And there's also a help forum as well. So if you're interested, if you want to calculate the transport properties in semiconductors and you don't want to have to use a lot of compute time, I encourage you to check it out. And if you have any questions, post them on the chat, on the help forum. So now we have a tool to calculate transport properties quite cheaply. I just want to change tack a little bit and show you how I've been using it to understand the temperature dependence of carrier mobility. So I spoke about mobility briefly, but I'll just remind you, mobility effectively tells us how quickly an electron or hole moves when it's pulled by an electric field in a material. And the way we obtain it is we take the conductivity, and then you can just divide through by the number of charge carriers, or the doping concentration, effectively. So really, ever since the first theories of semiconductors were developed, the temperature dependence of mobility has been used to gain insight into the fundamental kind of quantum behavior of materials. So in this really seminal work by A.H. Wilson in 1931, he developed expressions for charge transport in semiconductors under the assumption that lattice vibrations were the dominant source of scattering. And what he found was that under these approximations, you'd expect the mobility to have a T⁻³ temperature dependence. So effectively, as you increase your mobility, the temperature, your mobility drops with this dependence. And what was nice was that about 25 years later, his predictions went on to, well, his calculations went on to really agree very well with transport properties measured in N-type germanium. So this was some measurements done at Bell Labs, and here it's showing the experimental mobility, and this is the ideal T⁻³², and you can see there's some really nice agreement here. And I just have to say, this paper was really impressive. This work by Wilson was very impressive, because it was really the first time, I think, that semiconductors were really treated as valence and conduction bands separated by a gap. And it was the first time that, in semiconductors, impurities were treated as a source of free carriers, and actually that lattice vibrations were used to model the scattering. And it agreed with, it was very prescient work, and I think it agreed with the experiments really well. So basically, since Wilson's paper, the temperature dependence of mobility has been used as a signature of the dominant scattering mechanism in materials. So if you measure your mobility and you see it varies as this T⁻³², then typically you would assume that it has optical or acoustic deformation potential scattering, which is limiting your mobility. If you see T⁻⁻0.75, then this is considered an indication of polar optical phonon scattering. Alloy scattering has its own temperature dependence, and then impurity scattering has this positive temperature dependence. So as you increase the temperature, you expect the mobility to increase. Now, the thing is, all of these values were obtained from very simplified models of transport, only considering parabolic and single band structures. And unfortunately, I'd say that these limitations are often forgotten in thermoelectric studies, and they're kind of routinely applied, maybe when they're not appropriate. So now the thing is, in the last 10 years, we've really developed very accurate tools for calculating transport quantitatively. And I mentioned DFPT before. That's mainly implemented in these two packages, EPW and Perturbo. And what's happened is, just to show you how kind of accurate these approaches are, this is just some results on 3 semiconductors, gallium arsenide, silicon, and strontium titanate. These are 3 very different materials with different band structures, different scattering physics, and the DFPT approaches really agree both on magnitude and the temperature dependence as well. Now, the thing is, when these results started being applied, these methods started being applied to thermoelectric materials, there were some unusual observations. So tin selenide has long been considered dominated by acoustic phonons, and that's because its mobility shows this T⁻³ temperature dependence, and that's what I'm showing in this plot here. I think the experiments are these filled circles, these filled shapes. But when people ran DFPT plus Vanya on this material, they found that their calculations reproduces the experimental temperature dependence very well. But when they actually looked at the scattering physics, they found that polar optical phonons dominated the scattering, not acoustic phonon scattering, as what had been presumed based on this temperature dependence. And so this really raised the question, I think, does this temperature dependence of mobility actually tell us anything about the dominant scattering mechanism? And that's what I just wanted to look into with this work. And so to start with, I did a review of all DFPT plus Vanya calculations to date. where they provided the temperature-dependent band structure. And this is just where temperature-dependent mobility, sorry. And these are a summary of the results here. So on the x-axis, I've got the temperature dependence, and on the y-axis, I'm just plotting them against the effective mass just to try and separate these points out a bit. And in each case, I've indicated the dominant scattering mechanism by the color. So here, for example, this teal means polar optical phonon scattering, pink is deformation potential scattering. And if there were multiple mechanisms that were competing, then I've indicated them with half-filled circles. So I just want to draw your attention to two things. The first is that if we pick a particular mechanism, for example, polar optical phonon scattering, you can see, so here I'm just looking at these teal points, you can see that the temperature dependence really varies across a very large range. It goes from effectively minus 0.5 all the way to minus 3 just for this one mechanism. And the second thing is that if we take these idealized temperature dependencies that we would have expected from these early theories, I'm plotting them here for deformation potential scattering, so this is minus 3/2, and the polar optical phonon scattering. If these had any predictive power, we'd really see the points to be clustered around these lines, and you can see that there's effectively no clustering whatsoever. And so this was, after I made this was kind of the first indication that really this indicates that it's not safe to assume a scattering type based only on the temperature dependence. There's something else going on here. And so to investigate this further, I turned to AMSET and did some calculations using the AMSET package. So here I'm trying to go back to as simple as a picture as possible. So I'm performing AMSET calculations on a single parabolic band, an anisotropic band as well. So basically, this is going back to those idealized models. But here I'm using the full kind of scattering rate equations which we have available in AMSET. And what I found was that a single and the other thing I should mention is that I'm only including a single scattering mechanism here, and that's polar optical phonon scattering. And what I found was that a single materials parameter, namely the polar phonon frequency, by changing that, you can actually tune the temperature dependence across a really broad range. So if you have a small polar phonon frequency, you get a temperature dependence of -1. And as you increase that, you get a temperature dependence over -3. And these results were at low temperature. But actually, when you go to high temperature, you see, again, quite a large modulation, although it is reduced somewhat. So the phonon frequencies have a large impact. Now, I mentioned this is only polar optical phonon scattering. I hope I can convince you that we believe that actually this polar phonon, the phonon frequencies are actually responsible for the temperature dependence in all types of phonon scattering. So here I'm just going back to this summary plot of gallium arsenide, silicon, and strontium titanate. If we take gallium arsenide, for example, it has a polar phonon frequency of about 8. And if we read off, I plotted that here, if we read off about 8 on this plot, you would expect a temperature dependence of about -1.8 or 1.6. And that's really close to what we see in experiment, -1.7. Silicon, p-type silicon, has a very different scattering physics. It's not polar at all. And actually, in the p-type case, you're really dominated by optical phonon scattering. So if we take the average optical phonon frequency in silicon and read off from this plot, which is again determined just using polar optical phonon scattering, but we'll misuse it for now. If we read off the expected temperature dependence, it's about -2.5 or 2.4, which is again very similar to what we see in experiment. Strontium titanate, this has very complicated scattering behavior with polaronic effects, deformation potential scattering, and polar optical phonon scattering. The average which is really similar to what we see in experiment, so 3.1. So this kind of leads us to believe that actually, and confirms really our opinion, that phonon frequencies are the major factor that call the temperature dependence irrespective of the scattering type. We did look at other band structure effects, such as non-parabolicity. So here I'm looking at kind of non-linearities of the band structure away from the band edge. Also looked at anisotropy. These have some effect, but much smaller compared to the phonon frequencies. So far up until this point, with AMSET, I've just been calculating the transport properties in very simplified, idealized band structures. I wanted to understand whether the lessons that we've been learning kind of held for realistic materials and kind of realistic band structures. And so to do that, I looked at calculating a large number of mobility calculations. So in total, I did calculated the transport properties of 24,000 materials. Now, as I mentioned before, in AMSET, we need these common materials parameters, things like elastic tensors, in order to calculate scattering. Now, unfortunately, we don't have all of these materials parameters available for this many materials. So what I did was I trained machine learning models to predict these transport properties, so to predict, sorry, these materials parameters. So I took the elastic tensors, dielectric tensors, and Phonon frequencies from the materials project, and also calculated 3,000 deformation potentials for my own. And then I trained machine learning models on them using AutoMapMiner. So this is a package that we developed for automatic machine learning of material science data sets. And again, I think if you have to do some machine learning on some material science properties, I encourage you to check this package out, but I won't go into it today. And then I combined these machine learned materials parameters with 24,000 band structures from the materials project and calculated their transport properties using AMSET to come up with this database of mobility calculations. And this is just a summary of the results. Here I'm showing the temperature dependence limited by different scattering mechanisms, so polar optical and acoustic deformation potential I'll just discuss now. So there's 2 points that I want to make. The first is that, these are violin plots, and this effectively shows a histogram of the results. And so, the first thing is that this distribution for polar optical phonon scattering and the acoustic deformation potential distribution overlap entirely. If you had to pick a point in here, you wouldn't be able to distinguish which one it was in. And the second thing is that the kind of average temperature dependence across the entire distribution is very similar. So for polar optical phonon scattering, it's minus 2.1, and for acoustic deformation potential scattering, it's minus 1.6. This is at low temperature. At high temperature, it just gets even worse. So these distributions overlap even more now, and the average values for the temperature dependence of the entire data set gets even closer. So really, this is just exactly confirming, I think, what we saw in the DFPT plus Vanya data set, which is that it's basically impossible to determine the dominant scattering mechanism based only on the temperature dependence of mobility. You really need to take into account other things if you're going to determine what is dominating in your material. So lastly, I just want to say a few words on why I think this is important. And this is really mainly focused on thermoelectrics, but I think it has applications across other materials as well. So the point is really that this temperature dependence of T to the minus 3/2 has been used to justify very unphysical materials parameters. So here I'm just showing 3 materials, tin selenide, lead telluride, and bismuth copper oxyselenide, which are classic thermoelectric materials and were long considered to be dominated by acoustic phonon scattering based on their mobility dependence. And so based on that, in order to reproduce the experimental results, people had to fit very large deformation potentials to match the experimental mobility, so around 24 electron volts. Now, more recently, people have gone on to calculate these materials in more detail and have found that in each case, they're actually dominated by polar optical phonon scattering. And when you calculate their deformation potentials, they're much smaller, in some cases, almost an order of magnitude smaller. And when you consider that deformation potential scattering goes as the deformation potential squared, you can really see that you're getting a very incorrect understanding of transport in your material. Now, when you're, so the kind of second side of this is that the underlying mechanism of scattering controls the optimal temperature and carrier concentration needed to maximize thermoelectric performance. So if you're getting an incorrect picture of the scattering, then and you're basing your optimization efforts on that picture, it's going to be very difficult to optimize the performance to the ideal value. So that's my talk. I've introduced a new approach for calculating scattering in semiconductors and calculating transport properties. And then I've used that to understand the temperature dependence of carrier mobility. So I really hope I've convinced you that the temperature dependence of mobility doesn't indicate anything about the dominant scattering mechanism. And in fact, the temperature dependence is almost entirely controlled by the phonon frequencies and then to a lesser extent the band structure features. And I think based on these results, it seems like polar optical phonon scattering is much more common in materials than we've previously thought. So I'd like to thank my old group, Anubhav Jain and Junsu Park, and then the funding that I received for this work. And lastly, thank you very much for your attention, and I'll take any questions.
Great, thanks very much, Alex. Really, really interesting. I guess people will clap in, in the strange virtual way that we do. Yeah, really. I mean, both parts very interesting. I mean, both a very useful tool there for people to calculate their properties, and also some very thought-provoking comments about the temperature dependence, which looks like a lot of people have to think about what they're doing in their analyses. Do we have any questions from the audience? Just you can raise your hands or just shout. Just maybe an easy one while people are thinking is, I mean, you showed the gallium nitride where you were demonstrating that AMSET fits the data really well, but you had different contributions there. But and you're calculating ab initio, but presumably you need to assume something about the defect concentration or something in doing that fitting. So how do you decide those kind of contributions or the relative contributions?
Yeah, that's a good point actually. So for the defect concentrations, I'm just assuming that it's basically proportional to the carrier concentrations, which is fine, I think, in most cases. But if you have very high levels of compensation, then that's not going to be right. So yeah, the default behavior is just to say it's the same as the carrier concentration, but you can also input a defect concentration if you wanted to do that. Yeah.
I mean, I guess if you were comparing it to a very clean system, then you might think you have a lot of intrinsic carriers, and so that might not be true. I mean, obviously, depending on the temperature that you're at.
Yeah. Well, yeah, I think it's assuming that because that was a very pure system, I think you will still have to have some, like even those intrinsic carriers, they're going to have to be charged impurities in order to be donating those electrons in the first place. So I think the idea with the kind of pure system is that you really don't have very much compensation.
Yeah. Yeah. Sachin?
Yeah. Thank you very much for your nice talk. I just want to know lifetime, because I'm an experimentalist. So lifetime is one of the very difficult thing if your material is not PL active to find that value. So, but same point, I just want to know how exactly how can we overlap the both experimental and DFT things together, and how much it is accurate if we are not knowing the experimental the value of the lifetime, because there is a trap states, recombination process, many factors is there, and how can we consider that all factor in the DFT calculation?
Yeah, I'd say that AMSET is really the first level approximation to calculating scattering. We're not including things like recombination or kind of polar unhopping, or there's many other levels that you can go to get better results. This is just assuming band transport, where you're really limited by phonon scattering and I'd say kind of small levels of impurity scattering. But yeah, I would. If that situation describes your system, then it should be a pretty reasonable approximation. There's also some tools in AMSET for calculating grain boundary scattering and things like that.
Okay. Thank you. It's a very interesting talk. First time I saw somebody doing this kind of thing. Thank you.
Great. I was also wondering, you didn't show any bismuth telluride anywhere. Is there a reason why that's not included?
No, I do have results for bismuth telluride actually. It's a little bit tricky because it's a really small band gap material, and so you get what's it called? You get basically occupation of both holes and electrons, even at room temperature. So it's bipolar. Is it bipolar? Yeah. Anyway, it's a tricky case, but I think if you have to use very good experimental results. But when you do that, the AMSET agreement is quite good. Yeah, I think that's in the actual paper, but not in the slides.
I guess because the bismuth or antimony telluride alloys are, I mean, maybe the incumbent material of choice, right? So
no, yeah, definitely, yeah. But again, yeah, again, that's the other thing, is that I've not implemented alloy scattering, so that's going to be a whole another thing to think about. But yeah, I don't know how reliable the results would be if you just made a disordered cell and then calculated that band structure and fed that into AMSET. Maybe that would be a reasonable first approximation.
Mm-hmm. Yeah, interesting. Any other questions? I think it looks like we're all done. You've given people lots to think about, so maybe they'll come back to you with their questions to follow up, or maybe systems they'd like to calculate using AMSET. Looks like there's lots of interesting opportunities there. So thank you very much, Alex, for a fantastic talk. And